And I'm going to assume that out of the five, you're Catalin.
I'm Catalin, yeah. Okay.
Okay, so it's my pleasure to introduce Catalin Dima, who's going to give a talk on careful autonomous agents in environments with multiple common resources.
Okay.
And as Rafael mentioned, I will be here based in the 5 minutes at some point.
Okay, thank you. So my talk it's a talk related to this synthesis problem for an orchestration problem in which the multiple agents are supposed to interact in somehow, considering that they have individual objectives. So it's joint work with Rodica Condurache, who is at the University of Oualhadj, Madalina, Jitaru is here, who's our PhD student, Youssouf Oualhadj, who's my colleague from Créteil, and also invited Professor Bolzano, and Nicolas Troquard is here. Okay,
the one on the bottom is
okay. Okay, good. So the other way on. Good. Okay, so it's a talk about managing many resources in a multi-agent system, resources that are like water, pictures, whatever, which are supposed to be non-excludable. So everybody has access to these resources. They are supposed to be consumed or produced, and consumption might prevent or limit the other agents to consume the resources. And there's a whole history about studies related to how multi-agent systems can be can manage the behavior of can manage the competition on resources such that a successful management comes out of that. Okay, so our our research, our work is on algorithm management of these common resources, and the aim is to synthesize a controller strategy in which if the agents in the system behave rationally, and so if the agents in the system behave rationally, then the system behavior satisfies the objective of the controller, and the common resources are not depleted. And of course, it's an algorithmic approach in the sense that we identify some relevant classes of problems for which the synthesis problem is decidable, and we study its complexity. Okay, more concretely, so we have a setting in which we represent the system as a graph arena, so as an arena organized as a graph, a label graph in which we have some transitions between states, between the vertices of the graph. So the vertices of the graph belong to some of the agents. So the agents control the transitions, control the execution of some actions that are labeling that are the edges in the graph. And on each edge, there's some operation on the different resources. So for example, here we have a free-agent system with two resources, and each action, each transition in the graph modifies one of these resources by incrementing, decrementing, or leaving it as is. So we have three agents: the circle agent, the box agent, and the diamond agent. And the different objectives are modeled as some terminal states which correspond to the objectives of each agent. So we will also add at some point some quantitative objective as well, which is related to the behavior with respect to the resources. Okay, so how do agents interact? They interact by means of by deploying a strategy to interact with the other agents, which means that actually they have a plan that corresponds to that prescribe for them a specific action. That respective action is supposed to be executed considering some the agents observing some history of the system. And the particular case are memory strategies, memory-less strategies in which the agents execute a certain action, when the system is in a specific state, and of course is a state that is controlled by the respective agent. Okay, so now where rationality comes into play is the fact that agents might have different objectives, which is a little bit contrary to what Brian has shown us. So they are individuals, they are selfish. Each of the agents has a particular temporal objective, which can be represented by a linear temporal logic formula, which could be reachability, safety, or whatever. In our case, it would be a reachability objective, meaning that agent A is supposed to reach this state. So this is his objective. He's not happy if the system ends in the other states. The box agent is happy when the system reaches these two states, and so on and so forth. And rationality comes, in our case, as looking for a Nash equilibrium in which no player can unilaterally deviate and change his degree of happiness. Yeah. Okay, so let's look at a particular case in which there's no resource. So agents only are concerned by their temporal objective. So this strategy here, meaning that in first state, agent A moves right, agent B in his state moves right, and agent C moves right. This is not a Nash equilibrium because agent C, who is not happy about the system reaching the final state, which is here, could deviate, could execute this strategy, and then move to another, modify the resulting degree of happiness for himself. Huh? Now, this strategy, which consists of two black arrows and one red arrow, is still not a Nash equilibrium because in this case, B is not happy and he could change his strategy. No, I'm saying, no, this is, sorry. And that would the example was very different. Okay, this is a Nash equilibrium because agent B, even if he deviates, doesn't improve his objective. So this is okay. Now the classical setting of rational synthesis problem, which could be labeled as the cooperative case, is the setting in which we have this global arena representing the interaction of the agents and n objectives, one for each agent. And we also have a designated agent one, which is the controller of the system. And the quest is to search for a strategy profile such that when all the agents behave corresponding to this strategy profile, the resulting run satisfies the objective of agent one, and the strategy profile is a Nash equilibrium. Yeah? So it's a one fixed Nash equilibrium. Yeah. Okay, and yeah, good. Now, how can this be modified? So these, I'm recalling things that are there in the literature. How does this modify when taking into account the quantitative aspect of some resources, some quantitative measure of the resource degree, resource utilization. So we might have some careful agents and careless agents. So okay, this is meant to take into account the fact that there are two objectives, in fact, for each agent, and the agents might or might not be interested in the second objective. Yeah. So the first objective is their temporal objective, and the second relates to the degree of the resource. So we might have careless agents which bother only on their temporal objective, and we might have careful agents which would not deviate if the resources drop below to zero. Yeah. So the impact is that the deviations in the case of careful agents the agents could consider deviations which do not deplete the system resources, whereas the careless agent could deviate in any case. And the quantitative setting then is to define a strategy profile which still satisfies the objective agent one in such a way that the level of the resources of each resource stays above zero at any point. and of course is a Nash equilibrium for the whole system. Yeah, and now we have also flavors for all the other agents. So first of all, notice that agent 1 is supposed to be careful because the degree of the level of the resources stays below 0 in the resulting strategy. And anyway, the straight agent 1 is not interested in deviating since the play is satisfying its objective. But the other agents could be considered either careful or careless. So we can have various flavors for that. So let's look at what happens in so something that we presented last year, AMAS. What happens when we have a single agent, a single resource system? We still have the objectives which are represented here, and each transition either increments or decrements the respective unique resource. So in the case of agents other than the controller being careless, there is no careless solution for the rational synthesis problem. The idea being that well, agent 1 can pump any number of times in state A. The problem is that the behavior from the point of agent 1, in order for this behavior to be a solution, needs to reach this state. And so it means that at some point agent C needs to go right, but agent C is not happy about that because the resulting behavior is not satisfying his objective. So then agent C will deviate, and since agent C is supposed to be careless, doesn't matter, doesn't consider the resource, depleting the resource as important, then the resulting behavior is not Nash equilibrium. And of course, there's no other strategy profile which will satisfy agent 1's objective. On the other hand, if we consider all the agents as being careful, then this behavior here, this strategy profile here, is a Nash equilibrium. So agent A pumps once, so meaning that the resource starting from 0 reaches level 1 and then goes right, and then agent B pumps twice and then goes right, and agent C goes right. So the funny thing here is that the resource level when agent C reaches, when the system reaches agent C state equals 1. So this transition, which is still enabled, will not be taken by agent C because agent C is careful. So the resulting behavior is a Nash equilibrium. Agent C is not interested in deviating. Yeah? In some sense, careful agents can be controlled by keeping the resources as low as possible. Yeah, which is not very nice, but it's like that. Okay, so we have a lot of results, a sequence of results on various settings relating with a single resource. And now I'm going to give you what is in our paper. Yeah, good. So okay, so I'm going back to the original setting, the original example with 2 resources and 3 agents. And we can see here then that there is no solution, careless or careful, for this rational synthesis problem for reasons mainly related to the same situations that we had before. So first of all, agent A needs to reach the final state, at least the rightmost state here. So then agent A needs to pump at least several times, at least twice, in order for the decrements which are implied by agent B and C's actions to allow for reaching the rightmost state. But then, considering the fact that agent A needs to pump at least twice, the system reaches agent C state here with energy level which is at least with first counter being at least 2 and second counter being at least being 0, I think, or something like that. And so there's agent C can deviate and ruin the Nash equilibrium in that sense. Now, if we bound all the resources to some specific value, let's say 3, then there is a solution to the rational synthesis problem in the careful case, because okay, what does it mean to bound the resource level? It simply means that any increment when the resources reaches the upper bound does not impact the resource level. So in this case, when one of the resources reaches level 3, then any increment will leave the resource as is. And then we have this strategy here, agent A pumping 3 times, then agent B going right, then agent B going right, then agent C going right. And in this case, with this strategy profile, agent C, consider that he's careful, will not be able to deviate because he will drop the first resource below 0. And we have this behavior here. Okay. Now, going to the actual results. So first, the bad news is that the cooperative rational synthesis is non-decidable when we have at least 2 resources and 2 players. And the proof idea is that, well, we can encode some classical undecidable problem like, okay, by some intermediate coding as multi-counter automata, so reachability counter problem for multi-counter automata can be encoded as this problem. Okay, now if we go to bounded resources, so the good news is that the rational synthesis problem is decidable. Well, it's 2x time complete when the objectives are given as LTL formulas. Okay, it might be looking very as having a high complexity, but it's no more difficult than the LTL synthesis with a single agent. And the trick is that well, what do we need to do? Well, of course, we need to unfold the state graph into a finite state space, since all the resources are bounded by fixed upper bound, let's call it B. Then the state space goes exponentially. Yeah? So we have an exponential number of states with respect to the initial number of states, because we have an exponential here in terms of the number of the resources. But it's not ruining the complexity bound because we can rely on the fact that the synthesis problem for LTL objectives is in 2x time, but it's 2x time only in the size of the formulas and only polynomial in the size of the array. Okay, so what happens here is that we unfold the system graph. We then transform this problem of rational synthesis for resource bounded systems into rational synthesis without resources, and then use the algorithms that we have there. And the algorithms are 2x time, and they are 2x time considering the fact that they are only polynomial time in the size of the array. And since the lower bound is also 2x time by means of the cooperative synthesis problem, then we have a 2x time complete result. Okay, now hope I think. Okay, so what about the future work? So we would look at a non-cooperative case. What's non-cooperative? Well, cooperative in this case was proposing a strategy profile to all the agents, which means that they are supposed to follow that strategy, that profile, because they are rational and they know that by deviating they will not improve their outcome. Well, they might be not happy by the fact that they are imposed that strategy profile, so they might even consider any other rational behavior, and this makes the non-cooperative case, in which instead of proposing the agents of a strategy profile, ensuring we switch to the problem of ensuring that any rational behavior from all the strategies is satisfying the objective of agent one. And another question concerns the parameterized systems, where when we can leave some quantities of the system unspecified and synthesize some bounds on that. Yeah, so that would be it. Thank you.
Thank you very much for the presentation. We do have time for one or two big questions.
Thank you very much for an interesting talk. I was wondering, usually the corrigibility objectives, that you can kind of compute what the bound should be given the system.
Yeah.
So that kind of allows you to get decidability even if there is no bound. But in your case, as you mentioned, it's sometimes useful to keep the resources low because of the rational part of the synthesis that they can't deviate.
Okay, so first of all, if even if we look for reachability objectives in the case of several resources and unbounded resources, then we are still undecidable. Yeah. So if we are bounded, I think it would still be in X time, something like that, because reachability is decidable in P time, but we still have this exponential explosion in terms of state space. Yeah.
So yeah, so undecidability comes from possibility of deviation, and that you need to keep the resources down, so you don't have this monotonic property that you can achieve something with little resources.
No, I think undecidability really comes from the fact that with two resources and with two resources and deviations, we can play a little bit with simulating any Turing machine or whatever. Yeah, of course, the deviations are important.
So maybe a comment, right? So imposing a full strategy on an agent seems very restrictive, right? And so the work that I talked about the last edition, social laws, is the idea is to try to make as few restrictions as possible on the agents while still ensuring that the system behaves properly. So that no resources are depleted below zero or something like that.
So you mean having something like non-deterministic strategies in some sense?
So like eliminating very specific transitions.
But then the system is still non-deterministic. So
yes. It's fine if the system is non-deterministic as long as every behavior that is feasible under the restriction doesn't deplete the resources. There's been some work by Mike Woolridge and some of his colleagues doing some similar things with logic-based specifications.
I'm trying to transfer that for these multi-resources, but I think that even with that, having several transitions at a single state, we can just split that in having two transitions at this state by just replicating each state as many times as transitions have there. And then cutting one, just a single, see, so you still have undecidable segments. I think you will not get rid of that.
Probably not.
Okay, let's thank the speaker again.